Hello and welcome. Today, we're diving into a really fascinating question. How do companies that promise to pay for future disasters, actually predict what those disasters will cost? It's a world that pits the comfort of having one simple number against the messy reality of an uncertain future. Let's get into it.
Just think about it for a second. An insurance company has to put money aside today for claims that might not even happen for years, sometimes decades. How in the world do they land on a number for that? This is the core challenge of reserving, and the way we answer it has been changing in a really big way.
For the longest time, the whole game was about finding a single best guess. You can think of it like planning a trip and saying it's going to cost exactly $500, period. It feels super precise, right? But the real world just doesn't work that way. The new way of thinking is to embrace that uncertainty. It's about defining a range of possibilities, saying, okay, the trip will probably cost somewhere between $450 and $600. And that shift in thinking, well, it changes everything.
So, let's dig into that old way first, because understanding what's wrong with relying on just one number is absolutely key to seeing why this new approach is just so much more powerful.
So, traditional methods, and a famous one is called the chain ladder model, are what you'd call deterministic. They basically look at data from the past and assume the future will follow similar patterns. After a bunch of calculations, they spit out one single number, your best estimate. It's clean, it's straightforward, but it has a massive blind spot.
And here's the kicker. What if that one number is wrong? And by how much could it be wrong? Is it more likely to be too high or maybe too low? A single estimate gives you absolutely zero information about the risks surrounding it. It just gives you this false and frankly dangerous sense of security.
To really get why this matters, we have to lean into the messiness of the real world. The future isn't some clean projection of what's already happened. It's always full of twists and turns nobody saw coming.
And this is where things get, complicated. You've got sudden changes in the law, you've got inflation spiking out of nowhere, you've got totally new types of claims popping up. Even just shifts in how we as a society behave can have a huge impact. Any one of these things can completely wreck that single best guess, because your old data just has no way to account for it.
And this is where our hero arrives, stochastic reserving. Instead of trying to ignore all that uncertainty, stochastic methods are built to actually measure it. They don't just hand you a single best estimate. No, they give you a whole distribution, a whole range of possible outcomes. They show you the most likely result, but just as important, they show you how spread out all the other possibilities are.
And a cool way to think about this is that our total uncertainty, or prediction variance, is made of two parts. First, you have estimation variance. That's the risk that our model is kind of wrong. Did we pick the right assumptions? Then there's process variance. That's just the universe being random and unpredictable. The big idea here is that you have to account for both your own potential mistakes and the world's natural chaos.
So, how do we actually build these maps of what's possible? How do we chart out the future? Well, broadly speaking, there are two major ways of thinking about it.
On one side, you have what are called analytic methods. You can think of this like using a super complex math formula to directly solve for the answer, the average outcome and its variance. Then, on the other side, you have simulation methods. These are much more like running an experiment thousands and thousands of times. They use raw computing power to generate all these potential futures, to literally see what the range of results looks like. So one solves the equation, the other runs the experiment. Now, a really popular analytic tool is called the Mack model. What's so cool about it is that it's distribution-free, which is a fancy way of saying it doesn't try to force the future to look like a perfect bell curve or some other neat, tidy shape. It just hones in on two crucial things. What's the most likely outcome? And how wide is the spread of all the other possibilities?
Simulations, like bootstrapping, come at it from a totally different angle. It's actually pretty intuitive. Imagine you have 25 years of stock market returns. You just tell a computer, hey, create thousands of new 10-year histories for me by randomly grabbing years from my original data. For every single one of those simulations, you figure out the result, and when you plot all those thousands of results on a chart, boom, you've built a full, detailed picture of what's possible, right from the ground up. And that's really just scratching the surface. This just gives you a little taste of the toolkit actuaries are working with. You've got the Mack model we talked about, you've got other models like ODP, which you can then apply bootstrapping to. The point isn't to memorize all the names, but just to see that there's this whole array of really sophisticated tools out there, each designed for the specific job.
But, and I can't stress this enough, this is a really, really important but, no model is a perfect crystal ball. Even the most advanced, smartest stochastic methods have their limits.
This quote from our source material just says it all perfectly. Why? Well, think about it. These models are built using data from the past, and the past, by definition, has not experienced every single thing that could possibly happen in the future. So these models almost always tend to underestimate the true, wild, unpredictable nature of what's to come.
So it's so important to keep these limitations in mind. The models can underestimate risk, and they're especially bad with brand new types of claims that just don't exist in the historical data. And that's exactly why you always need human expertise and judgment to interpret the results. The model is an incredibly powerful tool, but it is not the final answer.
Okay, so after all that math and all that theory, why go through all this trouble? Why does actually putting a number on uncertainty matter in the real world?
Well, it matters because it informs basically every single major decision an insurance company has to make. How much cash do they need to keep on hand to make sure they don't go bankrupt? How do they prove to regulators that they're stable and know what they're doing? How do they price their products fairly? Even huge strategic decisions like which parts of the business to grow all depend on having a really honest, sophisticated understanding of risk.
So, if you take just one thing away today, let it be this. Stochastic reserving is really about a fundamental shift in how we think. It's about moving away from the false precision of a single, fragile number, and instead embracing a much more resilient and, frankly, honest view of the future, as a wide range of possibilities that we need to be ready for.
And that leaves us with one last question, one that goes way beyond just the world of insurance. If we accept that the future isn't one single point on a line, but a wide distribution of outcomes, how should that change the way all of us plan for it? In our businesses, in our finances, and even in our own lives? Something to think about.